How do you move a 15-ton granite block up a pyramid without a crane? Ancient Egyptians had a tool for that, and it wasn't what you think. We're about to dive into 8 ingenious tools that build monuments so precise you can't even slide a knife blade between the stones 4,500 years later. And the last one, it literally connected pyramids to the stars. Picture this. You're standing in a quarry, staring at solid granite that needs to become a perfectly shaped block. Your first tool isn't made of metal at all. It's dolerite, an igneous rock harder than the granite you're trying to cut. These dolerite pounders were basically the jackhammers of ancient Egypt, except instead of electricity, they ran on pure human muscle and determination. Teams of 60 to 70 men would rhythmically smash these hand-sized stones against the quarry face, creating shallow grooves around the perimeter of each block. The sound must have been deafening, constant pounding that could be heard for miles across the desert. Workers developed a specific rhythm, about 18 to 22 strikes per minute, that balanced power with endurance. Their arm bones literally show stress fractures from the repetitive impacts. The quarries at Aswan still bear witness to this ancient percussion symphony. You can see partially extracted obelisks and blocks with clear pounder marks, frozen in time when work stopped. Some blocks show grooves 12 inches deep, representing weeks of continuous pounding. The dolerite itself came from the desert regions east of the Nile, specifically chosen for its hardness rating of about 7 on the Mohs scale, compared to granite's 6. But here's where it gets clever. Once they'd created grooves around a block, they'd drive wooden wedges into the slots and soak them with water. The wood would swell, creating enough force to crack the granite along the predetermined lines. It's like controlled demolition, Bronze Age style. Each pounder would gradually flatten from use, but workers just rotated the stone to use a fresh surface, extending the tool's life without any maintenance. Simple, brutal, and devastatingly effective. The organization required for this work was staggering. Foremen had to coordinate the rhythm of dozens of workers, ensuring they didn't interfere with each other while maintaining maximum efficiency. Water boys constantly moved through the ranks, not just to hydrate workers in the desert heat, but to set the wooden wedges at precisely the right moment. Too early and the wood would dry out before the groove was complete. Too late, and you'd waste valuable working hours. Archaeological evidence from worker camps shows that pounders were personal tools. Many bear individual marks or wear patterns suggesting the same worker used the same stone extended periods. This makes sense. Like a baseball player with a favorite bat, workers would have developed a feel for their particular pounder's weight and balance. When a pounder finally broke or wore too small, it wasn't discarded. Smaller fragments were repurposed for detail work or crushing pigments for paint. Once you've got your rough blocks out of the quarry, you need tool number 2, copper chisels and adzes. Now, copper is actually softer than your car keys, so how do you use it to shape stone? Egyptian metallurgists discovered that if you cold hammer copper and then heat it in a specific cycle named annealing, you can make the edge hard enough to cut limestone efficiently. The process was remarkably sophisticated. Copper would be heated to about 932 degrees Fahrenheit, then hammered while cooling. This work hardening increased the metal's strength by up to 40%. But there was a catch. Too much hammering made the copper brittle, so smiths developed a rhythm of hammer, heat, cool, repeat, that maximized hardness while maintaining flexibility. A single chisel would only stay sharp for about 20 to 30 minutes of work, but the Egyptians set up an assembly line system. While one mason was carving, another worker was resharpening dulled chisels at portable hearths. Archaeological evidence from workers' villages shows they'd cycle through sets of 40 chisels, so the stonework never stopped. They had flat chisels for rough work, pointed ones for detail carving, and adzes, which are chisels mounted sideways on wooden handles for smoothing surfaces. The variety of chisel types reveals the specialization of the workforce. Broad, flat chisels, sometimes 4 inches wide, were used for rough shaping. These required less precision but more force, often wielded with wooden mallets weighing up to 6.6 pounds. Pointed chisels came in various angles: acute points for cutting deep grooves, obtuse angles for surface work. The finest chisels, some just zero point 0.2 inches wide, were used for hieroglyphic inscriptions. Adzes represented a revolutionary improvement in ergonomics. By mounting the blade perpendicular to the handle, workers could use their whole body weight and arm swing to smooth surfaces. Tomb paintings show adze workers in a characteristic stance, feet spread wide, tool raised overhead, bringing it down in smooth arcs that peeled away thin layers of stone like a plain shaving wood. Master craftsmen could achieve surface finishes so smooth they reflected sunlight, all with a tool that looks primitive to modern eyes. The precision these simple tools achieved is mind-blowing. The seams between blocks on the Great Pyramid are sometimes less than 0.02 inches wide. That's thinner than a credit card, achieved with tools made from metal softer than the stones they were cutting. For truly hard stones like granite and basalt, the Egyptians needed something more sophisticated. Enter tool number 3: copper saws with hand abrasive. The copper blade itself couldn't cut granite. It was too soft. But the blade wasn't really doing any cutting. It was just a delivery system for quartz sand. The engineering behind this is fascinating. Quartz sand has a Mohs hardness of 7, harder than granite at 6, but not so hard that it would immediately destroy the copper blade. The sand particles would embed themselves in the soft copper, turning the blade into what modern engineers would recognize as a lap, a tool covered in abrasive particles. As workers pulled the saw back and forth, these embedded particles would scratch parallel grooves in the stone. Workers would pour a slurry of water and sand into the cut while 2 or 3 people pulled the saw back and forth. The sand particles, harder than the granite, would grind away the stone while the copper blade simply guided them along a straight line. It's the same principle modern wire saws use, just 4,500 years earlier. Archaeological evidence shows saw marks on basalt flooring at Khufu's mortuary temple with curves about 0.16 to 0.24 inches wide, showing perfectly parallel striations. The saws themselves were engineering marvels. For large cuts, they used blades up to 6.6 feet long, tensioned in wooden frames like a modern bow saw. The tension was critical. Too loose and the blade would wander. Too tight and it would snap. Workers developed systems of wedges and twisted ropes that could adjust tension on the fly. Some saw frames found in tomb depictions show sophisticated mechanisms with multiple adjustment points. Experimental archaeology has revealed the optimal mixture: about 20 to 25% quartz sand by volume mixed with water, replenished every 5 to 10 strokes. In fine limestone, they could cut about 0.12 inches per minute. In granite, that dropped to just 0.012 inches per minute. Imagine the patience required to cut through a granite block when you're progressing less than 0.04 inches every 3 minutes. The logistics of saw operations were complex. A single granite cut might take days, requiring shifts of workers to maintain continuous operation. Sand had to be collected, sorted for uniform size, and stockpiled. Water was precious in the desert, so they developed recycling systems. Filtering used slurry to recover sand. The copper blades themselves were valuable, often recycled when torn too thin. Melted down and recast. Now we come to one of the most underappreciated tools in the Egyptian arsenal. Our fourth tool, the A-frame level, also known as the plumb bob system. If your pyramid is off by even 1 degree after 479 feet of height, you don't have a pyramid anymore. You have a very expensive pile of rocks. The A-frame was brilliantly simple: 2 equal-length wooden legs joined at the top, with a crossbar connecting them. A plumb line hung from the apex, and when it aligned with the mark on the center of the crossbar, you knew the base was perfectly level. But here's what's incredible. By changing three of these A-frames together across a 131-foot foundation, Egyptian surveyors could achieve accuracy within zero point 0.2 inches. That rivals modern laser levels. The mathematics behind this accuracy is stunning. Each A-frame could detect slopes as small as 1 in 1,000. By taking multiple readings and averaging them, surveyors could reduce random errors. They understood what modern engineers call error propagation, how small mistakes compound over distance. The solution was redundancy, checking and rechecking measurements from multiple angles. Survey teams left their marks all over pyramid construction sites. Small holes drilled at regular intervals served as benchmarks. Hieratic numerals scratched on blocks recorded elevations relative to a master datum. Red ochre lines snapped with cords showed where blocks could align. These marks reveal a sophisticated understanding of three-dimensional geometry that wouldn't be formally mathematized for another 2,000 years. They also used a plumb bob for vertical alignment, making sure walls rose straight up. The Great Pyramid's sides are accurate to within 1/15th of a degree. Without these simple gravity-powered tools, that precision would have been impossible. The plumb bobs themselves were works of art. Made from limestone, granite, or sometimes bronze, they were carefully shaped to be perfectly symmetrical. The weight typically ranged from 1.8 ounces to 17.6 ounces, chosen based on the application. Heavier bobs were more stable in wind but required stronger cords. The cords were made from twisted linen, sometimes reinforced with resin to prevent stretching. Archaeological finds show bobs with worn grooves where the cord attached, evidence of years of use. Moving on to tool number 5, the one that revolutionized Egyptian stonework, copper tube drills. While solid drills existed, the hollow tube drill was a game changer. Picture a copper tube spun rapidly by a bow drill, the same motion you'd use to start a fire. But instead of creating heat, you're boring through solid stone. The tube would be fed with that same sand slurry we saw with the saws. As it spun, it would cut a circular groove, leaving a stone core in the middle that could be knocked out. Old Kingdom sarcophagi show drill holes 9.4 inches deep and 2 inches in diameter. Modern experiments show a copper tube drill can bore through granite at about 0.24 inches per hour. The bow drill mechanism itself was a marvel of efficiency. The bow, typically made from flexible wood like acacia, was strung with twisted leather or rope. The drill shaft had a flywheel effect, a stone weight attached near the bottom that maintained momentum between bow strokes. This meant the operator didn't have to work as hard to keep the drill spinning. Some tomb reliefs show drills with multiple operators, one working the bow, another applying downward pressure, a third managing the abrasive slurry. These holes weren't just for show. Aligned drill holes allowed controlled splitting of hard stones. They created sockets for wooden lifting beams. They even served as reference points for the survey teams. The skill required was intense. One person pumped the bow while another steadied the drill shaft with a handheld cap, often sealed with beeswax to reduce friction and heat. The cores removed from these drilling operations weren't waste. They were valuable products. Granite cores became vessels, game pieces, even architectural elements. Nothing was wasted in pyramid construction. The drilling process also revealed the stone's internal quality. Cracks or color variations invisible on the surface would show in the core, allowing masons to reject flawed blocks before investing more labor. Here's where things get controversial. Tool number 6, ramps. Every Egyptologist agrees the Egyptians used ramps, but nobody can agree on what kind. The problem is that a straight ramp gentle enough for workers to haul blocks would need to stretch over a mile into the desert for a great pyramid. That's more stone than the pyramid itself. The engineering constraints were severe. A ramp suitable for hauling multi-ton blocks needed a slope of no more than 7 to 10 degrees. Any steeper and workers couldn't generate enough traction, even with the wooden sledges on wetted sand we'll discuss later. For the Great Pyramid's 479-foot height, A straight ramp would need to be over 3,280 feet long. The volume of material for such a ramp would exceed 90% of the pyramid itself. So they must have used either switchback ramps zigzagging up the sides, spiral ramps wrapping around the pyramid, or internal ramps built within the structure itself. The evidence is frustratingly sparse because the Egyptians dismantled their ramps after construction. Recent discoveries suggest internal spiral ramps with chambers found inside the Great Pyramids that could have housed hauling teams. But without a time machine, we can't know for sure. What we do know is that some kind of ramp system was essential, because you can't lift multi-ton blocks 450 feet in the air without them. Each ramp type had advantages and drawbacks. Straight ramps were simple but massive. Zigzag ramps saved material but created dangerous turns where blocks could slip. Spiral ramps distributed weight evenly but made the working area cramped. Internal ramps are invisible archaeologically but would have required extraordinary planning, essentially building two structures at once. Evidence for ramps comes from multiple sources. At the Pyramid of Mihdam, remains of construction ramps are still visible. The unfinished pyramid at Abu Rawash shows clear ramp attachments. Papyrus records from the reign of Khufu mention ramp construction and the enormous quantities of gypsum plaster used to create smooth-running surfaces. Worker settlements show wear patterns consistent with decades of trudging up and down steep inclines. Tool number 7 brings us to the levers and wooden rockers that actually move the blocks into position. The physics is simple: a long wooden beam, a fulcrum point, and mechanical advantage that lets one person move weight that would normally require 5. But the execution at pyramid scale is staggering. The levers themselves were typically made from Lebanese cedar or local acacia, chosen for their combination of strength and flexibility. A typical lever might be 13 feet long and 6 inches in diameter. The fulcrum point was critical. Too close to the load and you needed superhuman strength. Too far and the lever would bend or break. Egyptian engineers developed rules of thumb, literally, using body proportions to quickly calculate optimal fulcrum placement. Workers would rock a block up slightly on one side using levers, slide wooden supports underneath, then rock the other side. Rock, lift, slide. Rock, lift, slide. Repeat this process 2.3 million times, and you have the Great Pyramid. The precision required was extreme. One miscalculation and tons of stone would crush workers. Wooden rockers, essentially wooden quarter circles, allowed teams to roll blocks short distances by rocking them forward repeatedly. The coordination required for lever teams was like a deadly ballet. Tomb paintings show foremen using hand signals and rhythmic chants to synchronize movements. One person calling out commands, multiple teams working different corners of a block, assistants ready with wooden shims and supports. The margin for error was 0. A block that shifted unexpectedly could kill entire teams. Evidence for these techniques comes from unfinished pyramids where blocks are still sitting on wooden supports, frozen in time mid-lift. The human cost must have been enormous, but the mechanical advantage these simple tools provided made the impossible merely difficult. Wooden rockers represent an evolution of the lever principle. These quarter-circle wooden frames allowed workers to roll massive blocks by rocking them forward incrementally. Each rock might move the block just 4 inches, but that added up over thousands of repetitions. The rockers distributed weight across a larger surface area, reducing the chance of the wood splitting under load. Finally, we come to tool number 8, the one that still gives modern engineers chills: the merkhet, or star alignment tool. This wasn't just about building a pile of stones. The Egyptians wanted their pyramids to point true north, more accurately than most modern buildings. The merkhet was essentially a straight bar with a slight slot and plumb line. Astronomers would observe a circumpolar star, one that circles the north celestial pole, at its highest and lowest points. By bisecting the angle between these positions, they could find true north. The Great Pyramid is aligned to within 3/60ths of a degree of true north. That's more accurate than the Paris Observatory, built 4,000 years later with telescopes. The observation process required incredible patience and skill. Astronomers would work in pairs, one sighting through the merkhet while another marked positions. They understood that atmospheric refraction could affect observations, so they took multiple readings over many nights. The mathematical principles they used, though not written in modern notation, were sophisticated. They were essentially finding the midpoint of a star's apparent circular path, a technique that wouldn't be formally described until Greek astronomers centuries later. But the merkhet did more than just find north. It represented the Egyptian belief that their monuments weren't just earthly structures, but cosmic ones, anchored to the eternal movement of the stars. When you stood at the pyramid's base and looked up, you weren't just seeing a tomb. You were seeing a structure that would point to the same stars for thousands of years, long after the pharaoh's name was forgotten. The merkhet also served as a timekeeping device. By observing star positions, astronomers could divide the night into hours, crucial for organizing night shift work. This connection between monumental construction and astronomical observation created a feedback loop. Better buildings required better astronomy, which enabled even more precise buildings. These 8 tools formed an integrated system where advances in one area drove improvements in others. Better copper metallurgy meant sharper chisels and saws. More accurate survey tools demanded tighter construction tolerances. Improved hauling techniques allowed bigger blocks, which required stronger levers. But perhaps the most impressive aspect wasn't any individual tool, it was the standardization. Every measurement was based on the royal cubit, about 20.6 inches, subdivided into palms and digits. Cubit rods made of wood or bronze ensured that a block cut in Aswan would fit perfectly with one carved at Giza. This standardization extended to the workforce. A skilled mason could move from one pyramid project to another without taking their tools and knowledge with them. The modular nature of these tools meant they could be manufactured locally, repaired on site, and operated by workers with varying skill levels. Unlike some hypothetical mega machine that would need to be built for each pyramid, these tools were human scaled, portable, and endlessly reusable. A dolerite pounder used on Khufu's pyramid could be picked up and used on his son's pyramid decades later. The supporting infrastructure for these tools was equally impressive. Copper smelting operations at sites like Wattle El Jarf show industrial scale production. Tool manufacturing workshops have been excavated with specialized areas for different crafts. Storage facilities preserved tools between construction seasons. Even the wooden handles prone to decay in tomb contexts show standardized socket sizes, suggesting interchangeable parts millennia before the Industrial Revolution. When we look at these tools today, they seem almost impossibly simple. A rock for pounding, a metal blade for cutting, some rope and wood for moving, a weighted string for alignment. But that simplicity is deceptive. Each tool represents generation of refinement, countless small innovations that turn basic principles into precision instruments. The ancient Egyptians didn't have power tools or hydraulic cranes or laser levels. What they had was an understanding of fundamental physics, the patience to work stone millimeter by millimeter, and the organizational genius to coordinate thousands of workers using standardized tools and measurements. They turned the humblest of implements into the instruments of immortality. So here's my question for you. If you had to choose just 3 of these tools to build your own pyramid, which would they be? Drop your answer in the comments below. And if you want more about ancient engineering secrets that'll blow your mind, you know what to do. hit subscribe, ring the bell, because we're just getting started on the Nile Files' greatest building mysteries.